When writing programs that involve recursive data structures, such as linked lists or trees, you'll often find it's useful to be able to write a function that can produce such a data structure using a recursive process. And in this video, we're going to take a look at some common strategies for attacking these problems. We're going to extend the strategies we learned in the earlier lessons where we were working through a linked list recursively. Here, we're going to be producing a linked list recursively. And the function we're going to implement is one where we're going to be given two numbers as inputs and try and produce a sequence of nodes in a linked list that increase from our first argument to up to, but not including our second. So we're going to write a function that can produce a sequence of lists of linked list nodes. All right, so let's imagine our goal is sequence, right? So seq, and let's say we have something like 1 and 4 as our input arguments, and we're hoping that this returns a list where 1 is followed by 2, is followed by 3, and then it's not followed by 4, it's followed by none, right? So 1, 2, 3, none. Right? And that's sort of the goal of this function. We're trying to write a function that produces a sequence of nodes on our behalf. And we'd like to be able to do this recursively. So if we apply the strategies that we thought about before, rather than thinking about a complex case like this, we should start simple, start lazy, start with the easiest thing we can imagine. So the easiest thing we can imagine is probably something like sequence of 4, 4, right? Where, this is probably the easiest case we can address because we're going to return none, right? We're starting from our low argument and going up to the high argument, not inclusive of it. So our job is done here. We have no more work to do when our first argument that we provide to the first parameter of this function is equal to, in this case, we're going to return none and say that there's no more sequence for us to produce, right? There's no sequence here. And okay, well, what's another case? Well, another kind of edge case that we can imagine that's related to this one is, well, what if we did 5, 4? And for simplification purposes of this lesson, we're just going to assume that that's also going to return none. And so these are going to be the base cases of the sequence function that we're going to write together. All right. Now we need to start thinking about, well, what's the next simplest case we can imagine? Okay, if it's not 4, 4, well, I'm not even going to draw our number line because it's so straightforward. The next most simple case is not 4, but 3, 4, right? Or 4, 5, I suppose we could have done, but let's keep our high at 4 to keep this example consistent. So, okay, if 4, 4 is going to return none, and that's a base case, well, what's the next step that you can imagine being the next easiest thing to take on? And that's sequence from 3 to 4, right? And we know what we ultimately want this to produce, right? We ultimately want this to produce 3 followed by none, right? Well, the key tip of trying to write a function that can produce a recursive structure is don't worry about what comes after, right? We're going to leave that problem to the recursive process. What your focus is on solving and implementing a recursive process that produces a recursive structure is just figure out what you need to do with the current subproblem and then leave the rest to recursion. So in this case, what we're hoping to do is say, okay, we're saying we're going to result in the current value of our low parameter, which is 3, followed by whatever the recursive result is of sequence 4, 4, right? So the next step that we're going to make here, or we could have said low plus 1, which in this case would have been 4, right? And ultimately we know, like we've already solved that subproblem before, we know that's going to give us none. And if sequence 4, 4 results in none, then we've correctly solved this, right? Well, what's the next most challenging case we can imagine? Well, you can imagine what's sequence of 2, 3, right? Or sorry, 2, 4. Let's keep the 4 the same. Well, again, our focus is what is the way that we can solve the front of this problem that we're currently on, or the current subproblem. And that's going to be 2, right? And what's 2 going to be followed by? 2 is going to be followed by recursion, right? And so we're going to recur and say, okay, the sequence of 3, 4, right? That's what we want. The next, what comes after 2 is the result of the sequence of 3, 4, which we know, having just done that, right? That's actually going to result in a value of in a node whose value is 3 followed by none. Okay, so now that we have a feel for this, and these are our recursive cases, and I should point out that we didn't actually do anything different between these two cases. We just did this for illustrative purposes, but notice both of them did the exact same thing. They said, let's solve the problem for the current subproblem, and then leave the rest of the problem to recursion. All right, so this was our subproblem. And this is our recursive step for the rest of the problem. Right? And this is going to be a general technique that we can apply in many different places. Okay, so now that we've got an overview of how we might do this, let's take a look in VS Code of how we might solve it. So we're going to continue on from the node class that we set up in the previous examples, and let's go ahead and write a skeleton for this sequence function. All right, so I'm going to define a function named sequence, and the first value here is going to be the low parameter, and it's going to be an integer value. And the second parameter is the high value. That's also an integer parameter. And it's going to return. And what is it going to return? Well, let's think about this. We wanted to return nodes, but notice here in our base cases, we ultimately need to be able to return none. So if we're either going to return a node or none, we need this to be an optional node return value type, right? So let's take a look at that. So this will return an optional node. Okay. And what was our base case? Well, our base case was when the low parameter, right? So if we think about, this is our low parameter and our high parameter. When our low is equal to or greater than or equal to is the way we like to think about this when we're programming. If our low parameter is greater than or equal to high, then what we're going to do is we're going to return none, right? This is our base case. And I should have added a doc comment here for this to be a good skeleton function and another extra line there. Okay, so our documentation here is return sequence of nodes between low and high, not inclusive of high, all right? Okay, so we've returned none in our base case, and now we have our recursive case. Right? And we're going to break this recursive case down into a few important steps. Ultimately, we could simplify these into one single line of code when we're done, and we'll take a look at that. But I'm going to encourage you, before worrying about conciseness, to worry about clarity first. And so for clarity purposes, we're going to say, all right, what is our subproblem? Right? So our subproblem is, what is the integer of the current node that we're working on, that we're trying to produce, right? So the subproblem that we're trying to work on here is low, right? So that's the current value of our low parameter. And if we want to remind ourselves why this might be, okay, so in the case where our base cases are handled, so we know that our low parameter has to be less than our high parameter. So let's imagine this simple case where 3 and 4. Well, our subproblem is thinking about what's the thing that we need to do to solve just this one step of the problem, right? And we're thinking about the number 3 here because we're using that low parameter in this instance to be the current solution to the current subproblem we're working on. Okay, well, now we need to think about, well, what's the recursive step for the rest of the problem? And that's going to be sequence, where we take our current low, which was 3, and add 1 to it, right? So I'm going to set up one more variable here that's thinking about the rest of the problem. And this is going to be an optional node, right? Because it might be empty. It might be the empty list. And in this case, if we think about just the very first time we called this, were 3 and 4. When we make this recursive, call it a sec. So sec plus is low plus 1 for our first argument, and high for the second. We're going to keep high the same. All right. So we solve our subproblem. And in this case, it's a very simple, we're not actually doing much processing. We're just saying, all right, this is our counter. Low is our counter parameter. And then for the rest of the problem, we are going to leave that and hand it off to recursion and let recursion take the wheel, right? So here we're being sure that we're changing something about our arguments to ensure that we're moving closer and closer to our base case, right? So we're increasing our low parameter by 1. Ultimately, it's going to become greater than or equal to high at some point, right? Okay, so we've done that. And now how do we form our return value? So our return value is going to be a node, right? We want to produce a node where what is the value inside of our node? Well, that's the solution to our subproblem. And what is the next node in our list? It's going to be the rest of the list, right? And so here we're recurring and we're saying, okay, go solve the next subproblem, go solve the next subproblem until you reach the base case. And if we were to trace through this with an environment diagram and we were to look at, okay, once we reach our base case, we know that we're many frames deep into this recursive problem. And as we start returning our way out, our list starts becoming built up where each time we return, we're returning a node who's connected to the rest of the list that came after it. Right? And we'll try illustrating that in just a second. But let's go ahead and convince ourselves that this is actually going to work. So I start up Python. And from exercises.ex06.linked list, I'm going to import everything, right? And oops, I spelled something wrong. I forgot a D. Okay. And now what we can do is try sequence from, let's try the simple case, 4 to 5, right? And notice we have 4 to none. And actually, if we want to carry the same example we were using 3 to 4. And I have an extra parenthesis there. 3 followed by none. That seems correct. Well, are we actually doing this correctly for a longer list? 2, 3, none. That seems like it's working, right? So what about 0 to 4? Each time we solve one subproblem, we go and we figure out, well, what's the rest of the list as a recursive step in the process, all right? So if we were to try and think about how to, I'm going to clear this part of my screen out really quickly. What do the sequence of steps look like to get us from where we started to where we ended up and all the way returned back from the first call to sequence? So let's imagine a call like, let me switch colors here. It's a little hard to read. Let's imagine a sequence call that's something to the effect of 2-4, right? What is sequence of 2-4 going to do? Well, we're not going to hit the base case here, right? Sequence of 2-4 is going to result in low being 2, right? And the next part of that being sequence of low plus 1, which would be 3, 4, right? And so, okay, well, now we need to go figure out what is sequence of 3, 4. That is going to be, it's not the base case, right? So our subproblem is that's going to be 3, and that's going to be followed by the sequence of 4, 4, right? And so when we get to the sequence of 4, 4, what's that going to be? Well, that actually is our base case, right? So that's where we are going to hit low greater than or equal to high, and that's going to be none, right? So once we know what one of these values is in our, once we've hit a base case, we start returning that, right? So sequence of 4, 4 is actually none. Okay, well, what does that mean? If sequence of 4, 4 is actually none, that means sequence of 3, 4 is going to return a node where we're taking our subproblem, right? And we're connecting it to the rest, which was of this list, right? So now sequence of 3, 4 just evaluated to, this list, right? So when we get back to the frame where we're trying to figure out what is sequence of 2, 4, well, subproblem is going to be 2, right? And rest is going to be 3 followed by none. So this would be, when we create the node, it's going to be 2, 3, and then none, right? And I would encourage you to try tracing this process out in a recursive environment diagram, frame by frame, if that sort of intuitive high-level explanation doesn't quite make sense. The key idea, as one more brief illustration, is if we imagine, okay, so 2, 4, and then 3, 4, and then 4, 4, right? If we think about what is the end of this when we actually return none here. So this is none. So, that call returns none, right? And when we are at 3, 4, we're saying we're going to return a node where we're saying 3, and the rest was what came before it. And that's going to be returned back to, the problem where we're saying, okay, 2 is going to be connected to what came before it. because of the way that we are structuring this, this return value. More generally, what we're saying is when building a list recursively, construct a new list where the current subproblem is followed by the rest of the problem processed recursively, right? And I mentioned that we could rewrite this to simplify it just a little bit, right? So notice that these two lines, I might even just comment them out. Comment. We're returning the current subproblem, the current solution to our subproblem, which in this case, we're just counting up, right? So low is always the current solution to the subproblem of counting up, because each time we make our recursive step, we're going to increase that parameter, followed by a sequence of low plus 1 and high, right? So we actually could have written those two lines above it as a single return statement where we're constructing a new node where the current solution to our subproblem is followed by the rest of the problem processed recursively, right? This being said, I think when you're getting used to thinking in this way, setting up some explicit variables like we did to begin with is probably more helpful than trying to be terse, right? And trying to force yourself to think about, okay, what is my current subproblem, and how do I know what to do next, all right? So this was a quick look at constructing recursive structures using recursion, and this strategy of process the first thing and then construct a new node and a new list where that's attached to the front of whatever comes after that processed recursively will ultimately bring you down to a base case and build up a list or a recursive structure programmatically. And you could do this with trees and other data structures as well.